So welcome to the conference. Thanks so much for coming. This conference is a part of a long-standing collaboration between the Applied Ethics Center at UMass Boston and the Institute for Ethics and Emerging Technologies. My name is Cody Turner. I'm a postdoc at the Applied Ethics Center. The theme of my fellowship is essentially on the philosophy and ethics of brain-computer interfaces. And the idea behind this conference is to bring together different voices from industry, from medical research, from academia, to talk about the ethics, risks, and use cases of brain-computer interfaces. The focus is on interdisciplinary collaboration. We think this is especially important when you're talking about something like brain-computer interfaces that really exist at the intersection of different fields: neuroscience, law, philosophy, computer science, etc. And so the kind of purpose of my opening remarks is I'm going to kind of set the stage for the rest of the conference, introduce brain-computer interfaces, make some distinctions between different kinds of brain-computer interfaces. But first, I just kind of wanted to highlight some of the work that I've been doing as a part of the fellowship focused on brain-computer interfaces. So some of the stuff that we've been doing is we have an Ethics in Action podcast series on brain-computer interfaces, where we've been interviewing different experts from different fields who are working on BCIs. I'm going to kind of highlight some of those conversations in my opening remarks, in addition to kind of outlining the landscape of brain-computer interfaces. We have the Institute for Ethics and Emerging Technology Substack, where I have a Substack article on brain-computer interfaces. Jay's been writing a lot of articles, some of which touch upon BCI issues. We have an in-progress white paper on brain-computer interfaces and mental health. And this is a kind of follow-up from a white paper that the IEET wrote before my tenure here on AI and therapy, right? So we've already have like a track record of a white paper on technology and mental health. So now we're writing a white paper specifically geared towards brain-computer interfaces and mental health. I'm also currently the editor of a de Gruyter volume titled The Ethics and Politics of Neuroenhancement, Brain-Computer Interfaces and Neurotechnologies. So this is the third volume in a series that we've been working on with de Gruyter on the politics of human enhancement. In a second, I'll just kind of give you a taste for some of the chapters that we have folks writing for that. And then next year, we also have planning a larger kind of multi-day conference on brain-computer interfaces. So like a larger version of this conference, essentially. So this is some of the things that we've been doing as a part of this collaboration between the Applied Ethics Center and the Institute for Ethics and Emerging Technologies on BCIs. The white paper, just to say a few more words about that, right? It covers technical foundations, some of which I'll about to summarize, current therapeutic applications of BCIs in the realm of mental health, neurofeedback for depression, closed loop stimulation for anxiety, also enhancement applications, clinical evidence, efficacy benchmarks, ethical frameworks for implementation, that kind of thing. And then, like I said, just to give you some taste of some of the chapters that we have folks working on for this de Gruyter series. There's a chapter on brain-to-brain interfaces and collective identity, BCIs through the lens of the extended mind theory, BCIs in military research, engineered emotions, the ethics of emotional enhancement, brain-computer interfaces, and social inequality. So it kind of it covers the gambit of a lot of different issues on BCIs, specifically in the realm of cognitive enhancement. Okay, so like I said, the rest of my remarks here before I hand it off to Jay is really just kind of setting the stage for the rest of the conference, defining brain-computer interfaces, making some distinctions, and like I said, highlighting some of the conversations that we've been having on our podcast series on BCIs. So just to start at the most kind of basic level, the official definition of what a brain-computer interface is from the National Institute of Health: a computer-based system that acquires brain signals, analyzes them, translates them into commands that are relayed to an output device to carry out a desired action, right? So the key characteristic on this definition of brain-computer interfaces is they enable people to control external devices, right? Just using their brains without using motor capacities. And there are three basic kind of elements that any brain-computer interface really has, right? There's electrodes, there's a signaling command processing unit, then an application device, right? So, and there's two different basic kinds of BCIs that people distinguish in conceptual space: non-invasive BCIs and invasive BCIs, right? So in non-invasive BCIs, you have the electrodes that are placed on the forehead or the scalp. Invasive BCIs, they're implanted within or below the brain's cortical surface, right? So implantation as opposed to just on the scalp. And there are trade-offs with each one of these kinds of brain-computer interfaces, right? In the case of, broadly speaking, we can say in the case of invasive BCIs, limitations are there are surgical risks, potentials for scarring, that kind of thing, but higher signal quality and more precise capacity to measure brain signals. In the case of non-BCIs, there's lower surgical risks, cheaper, but potentially less precise measurements and lower signal resolution. So a kind of basic distinction between invasive and non-invasive BCIs. And I should say this isn't necessarily like a stark binary, it's more of a spectrum, right? So you can have BCIs that are in the middle of the spectrum, right? Kind of semi-invasive BCIs that are placed somewhere between the skull and the brain surface, right? So again, basically you have these electrodes, they're invasive or non-invasive, they're detecting and analyzing neural activity, and then some signal processing unit is converting that neural activity to a command that the application device then carries out into a technical action. That's the basic idea. And this isn't science fiction, right? There's tons of prominent companies working both in the invasive and non-invasive BCI space. One of our keynotes today, Adam Molnar, is one of the co-founders of Neurable, a Boston-based company working on consumer applications for non-invasive BCIs. So we'll hear more about that later in the conference. I also thought it would be helpful just to briefly distinguish brain-computer interfaces as I've defined them from other technologies within the broader neurotechnology landscape. So you can distinguish BCIs from neuromodulation technologies and neuroimaging technologies. All these images, by the way, I kind of created with ChatGPT. Neuromodulation technologies, right? These are technologies that broadly target stimuli, deliver targeted stimuli to specific brain regions. So an example would be deep brain stimulation. I'll say a few more words about that in a second, where you have implanted electrodes delivering electrical impulses to treat conditions like depression. Transcranial magnetic stimulation. Unlike brain-computer interfaces as I've defined them, neuromodulation devices primarily send signals to the brain, but don't necessarily read neural activity or allow you to control some external technological device. Neuroimaging technologies that monitor and visual brain structures or activities. So things like functional MRI. Unlike BCIs, neuroimaging primarily read from the brain, but again, aren't designed for real-time control of external devices. And these three categories within neurotechnology, brain-computer interfaces, neuromodulation technology, neuroimaging technology, they're not mutually exclusive, right? So there's tons of overlap. You have EEG systems that are used for both neuroimaging and BCIs. And a lot of emerging technologies combine these different features, right? So for example, a closed loop deep brain stimulation device with neural recording capabilities. So yeah, that's just kind of like a broad landscape of BCI technologies. I just wanted to quickly highlight one of our podcast episodes, just kind of zooming in a bit more on the non-invasive BCIs. We had a great podcast episode with Professor Jose de Millán. He's professor at the University of Texas at Austin, where he runs the Clinical Neuroprosthetics and Brain Interaction Lab. And he talked to us about the work he's doing on personalized neuroprosthetics, right? And this idea that brain signaling is a skill. So just to read a quote, he says, the main thing we've learned is that people here have to be taught how to change their brain signals. Our brain has evolved to control our body, not to relay signals to computers. Once we can teach people that skill, and it really is a skill, that's when we see incredible advances. And he's doing a lot of work on different kinds of non-invasive brain interfaces, including non-invasive brain-controlled robots, non-invasive brain-controlled wheelchair systems, BCI applications in telerobotic surgery, and even exploring enhancement applications, non-invasive brain-computer interfaces as like a driving system. That's a really fascinating study. I wish I could talk more about that, but don't really have time. Just to say a few more words about deep brain stimulation as a kind of neuromodulation technique. So deep brain stimulation, as I briefly mentioned, it involves implanting electrodes and delivering electrical stimulation to specific areas of the brain. And it's used for both neurological and psychiatric use cases. It's really an established treatment for neurological use cases, motor disorders like Parkinson's, essential tremors. For psychiatric conditions such as depression, OCD, addiction, it's really more experimental. And we were talking with Frederick Gilbert, who's done a lot of work empirically and philosophically on some of the more experimental use cases of deep brain stimulation. And a few interesting pressing ethical concerns that I just wanted to highlight from that conversation is one thing that we talked about with him is how deep brain stimulation, in some cases, there can be post-operative adverse phenomenological effects, where patients who use deep brain stimulation for depression will experience feelings of self-estrangement, sometimes hypersexuality, sometimes suicidal ideation. And there's tons of ethical concerns surrounding this regarding like authenticity and questions of identity, also in questions of informed consent. And one thing I think is important here is informed consent, not just in the case of BCI implantation, but also in the case of BCI explantation, right? So there have been real cases that Frederick Gilbert talked to us about where a patient gets deep brain stimulation, they're having post-operative phenomenological adverse effects. So the recommendation from the doctors is, okay, we need to explant this. But in some cases, the patients have said, actually, no, I don't give my consent to explantation. So there's like a lot of kind of murky ethical discussions to have there about what informed consent means in the case of explantation. There are other kind of more clear-cut cases where the tech company just goes bankrupt. So there's forced explantation for that reason. This is a condensed history of BCIs. I think I might skip this just for the sake of time. I guess I'll just highlight a few. I think Adam's probably going to give a more detailed history, especially when it comes to EEG. 1924, just to kind of give you a glimpse of the history of this technology, you have the first human EEG that laid the groundwork for modern BCI technology. The term brain-computer interface was coined in 1973 by Jacques Vidal. In the 2000s, that's where you start to see the kind of emergence of more invasive BCIs and implanted electrodes. You have the first enhancement BCI use cases in like 2007 with the company NeuroSky. It released what's called the Mindset. I think that's the first like official enhancement BCI that was on the market. And yeah, pretty much from the 2010s to present, there's kind of the growth of more commercial consumer grade BCIs. But again, very brief snapshot history there. It can be traced back to 1924. So we're talking like a century this technology's been going. I want to just quickly say a few words about the distinction between enhancement and therapeutic BCIs, right? So in addition to being used for therapeutic use cases, there's also this potential of enhancement use cases. And not just potential, like I said, there are already enhancement BCIs on the market. There are at least three holy grails of like BCI enhancement that I think you can distinguish in conceptual space. One, enhanced computer-human interaction, right? So BCI technology that could dramatically increase the bandwidth of information transfer between your mind and computational devices, right? So imagine not having to actually like click on use sensory motor interaction to engage with a computer, but just using your mind, you could bring up your email or something like that, right? Enhanced human-human communication, right? Brain-to-brain interfaces that could enable some kind of technological version of telepathy where thoughts and conscious experiences could be shared among people. Direct neuromodulation, right? Neuromodulation, not just for therapeutic use cases for treating things like depression, but actually enabling precise control over brain states, right? Allowing for like on-demand enhancement of mood, focus, creativity, that kind of thing. And I think it's worth pointing out that the boundary here between therapy and enhancement is going to be objectively fuzzy, as it is in general, right? So just kind of give two cases to illustrate that fuzziness. Transcranial direct current stimulation, right? It's used for depression, pain, stroke rehabilitation, that kind of thing. But it's now being explored for working memory enhancement, right? So you can imagine someone with borderline cognitive decline, and they use this transcranial direct current stimulation to enhance their memory. Is that a case of therapy or is that a case of enhancement? It seems to be in this kind of objectively fuzzy boundary case, right? Or neurofeedback techniques, someone with borderline ADHD symptoms who uses neurofeedback to improve their focus. Again, it seems to be kind of a case of not clearly enhancement, not clearly therapy. Okay, a few more remarks, so then I'll hand it off to Jay here. So when you start to think about these three holy grails of BCI enhancement, it becomes immediately pressing how responsible regulation in the space is, right? How important that is. So one of our podcast conversations we had with Raphael Yuste. He is a professor at Columbia University, and he has done revolutionary work on devising new kinds of neuroimaging techniques, particularly two-photon calcium imaging and holographic microscopy are two of the pioneering neuroimaging techniques that he's responsible for. And these techniques have allowed him to garner empirical evidence for what he calls neural ensembles, like groups of neurons that function as collective emergent fundamental units of computation in the brain, right? And he has empirical evidence for these via these kinds of neuroimaging techniques. And he had what he called to us an Oppenheimer moment in 2011, right? When he discovered he could control mice's minds by activating specific neurons with a laser. He was initially very excited about this innovation because of its potential for treatments like, schizophrenic hallucinations. But he quickly realized the profound ethical implications here regarding things like, mind hacking, mind reading, similar to, Oppenheimer's realization of the implications of the work that he was doing in theoretical physics like a century ago. And so following this ethical kind of realization, this Oppenheimer moment, he assembled prominent scientists to propose a brain activity map project that was explicitly modeled after the Human Genome Project. And the vision was to develop technologies capable of recording activity from every neuron in brain circuits. This proposal was adopted by the Obama administration in 2013, known as the Brain Initiative. There's currently, I think it's the largest scientific effort in history to map the brain. And Raphael Yuste also talked to us about what he calls the Neural Rights Foundation that he's founded. And he thinks that this is, an important part of safeguarding brain data in the age of brain-computer interfaces. And the Neural Rights Foundation advocates for 5 key neural rights: the right to personal identity, the right to free will, the right to mental privacy, the right to equal access to mental enhancement, and the right to protection from algorithmic bias. And it is worth mentioning that there's an entire debate in neuroethics right now surrounding this idea of neural rights, right? Where proponents of neural rights think, look, brain-computer interfaces and brain data, it's such a unique kind of data that we need kind of new rights to protect it, right? It's not like any other kind of personal data. It facilitates the possibility of unique kinds of ethical transgressions like mind hacking, that kind of thing, brain control. And for that reason, we need new neural rights. I just want to read a quote from Anita Farani, sorry. So in addition to Yuste Anita Farani, she's a philosophy professor at Duke University. She also is a strong proponent for neural rights. She proposes the concept of cognitive liberty in her book, The Battle for Your Brain. And it's worth mentioning that Yuste and his supporters, they've achieved important legal victories. So back in 2022, Chile became the first country to actually ratify neural protections through a constitutional amendment in their country. But there is a case against neural rights, right? People against neural rights will say, like, look, brain data, it's very similar to kind of other kinds of sensitive data like genetic data. Maybe we don't need like a new conceptual category of rights here. Maybe we can kind of extend existing privacy rights frameworks to cover brain data. People who are against this new concept of neural rights will talk about the idea of rights inflation, right? If we create all these new kinds of rights at a certain point, we're devaluing the concept of human rights in general. One of the philosophers who's kind of on this side of the argument is Stephen Rainey, who we also talked to in one of our podcasts, who has a recent book called Philosophical Perspectives on Brain Data, where he outlines this case against novel neural rights in more detail. But so there's a lot to kind of legally adjudicate here. Regardless of where you stand on this legal debate, whether we need this new category of neural rights, you can see how brain-computer interfaces threaten to exacerbate a lot of the existing digital ethics threats, right? Again, neurohacking is a new kind of computer hacking. And there's all kinds of different kinds of neurohacking at different stages of the BCI process. Neurocapitalism is a new kind of surveillance capitalism, right? The digital economy right now governed by this logic of what Shoshana Zuboff calls surveillance capitalism, where they take your data, they create these personality profiles, they sell it to advertisers. I mean, imagine just that kind of apparatus of surveillance capitalism being including brain data and how much more knowledge they could get on you with this brain data than they already have. There's a lot to be concerned about. And one of the biggest things to be concerned about is social equity and access, right? As with any emerging technology, it's always the richest people among us that get access to this first. So you can imagine the already wide social inequality in our society being exacerbated further, right? With the kind of dystopian enhanced haves, not enhanced have-nots. One last conversation that in our podcast series that I wanted to highlight was with Sarah Goring. Sarah is a professor of philosophy at the University of Washington. She leads the program on ethics and the disability studies program. And she has started what she calls the BCI Pioneers Coalition, right? Where the basic idea here is to develop brain-computer interfaces that, instead of following what she calls a technology push paradigm, is really governed by a needs pull logic, right? So not just developing technology because we can, but actually developing technology that's responsive to the needs of actual disabled people who need it. And part of what it means to follow this paradigm is including those disabled people who actually have BCIs within the research process, within the design process. And so this is her idea of BCI pioneers, right? The BCI pioneers being the actual people who have BCI for disability reasons, who are participating in her research as research participants and are actively informing the design process in a way that they don't usually get included in the design process. So I think this is an important effort when you're talking about equity in the BCI space. Then I'm going to skip over this for the sake of time, but I think brain-computer interfaces are poised to influence all kinds of different social domains, from religion to sports and education to the workplace, healthcare, which Dr. Young will be talking about in more detail, the military. Just as there's an arms race with respect to AI, there's also a BCI arms race, particularly between the United States and China. I think right now the United States kind of has a lead here in that it has a greater kind of market share, but China has a lot of advantages compared to the United States when it comes to BCIs. They have large colonies of research monkeys that they use. They have generally a culture that's more okay with the idea of having their data tracked. So I know there's one company in China where I think it's a train drivers. They're mandating that the train drivers wear EEG headsets to kind of monitor their attention levels when they're on the job. That's the kind of thing where you could imagine there being kind of staunch privacy objections in the United States. And this competition is not just economic, right? It's military too. Both countries see potential military advantage to be derived from brain-computer interface technology. So yeah, I mean, Raphael Yuste, to kind of address this global arms race problem, he's also created what he calls the International Brain Initiative, which is, brings together different countries to compare ethical frameworks, and with the idea that we should try to create these technologies to collectively benefit humanity instead of just being adversaries. And yeah, I mean, you might think like there's a lot of reasons to despair: this geotechnological arms race, the threats of neurocapitalism, compromise authenticity, increased social inequality. I think it's important not to kind of fall victim to an attitude of technological fatalism when it comes to brain-computer interfaces, or any emerging technology for that matter. I think, just to read a quote from Robert Mark Simpson, he says, when speaking of social media, technologies and practices that bubbled into existence less than 2 decades ago are being imaginatively reified as nailed-in load-bearing structures in humanity's household, as opposed to movable cultural furniture. So his point is that although social media has become a permanent fixture in our society, it's still relatively new, and we can shape it and decide whether we want it at all. And the same is true with BCIs, right? We shouldn't regard this as like this incoming technological wave that we're all just going to be bowled over by. No, it's a technological opportunity that we can shape to our values, guided by a value-sensitive design approach. And I think it's important that there's also public literacy around BCIs. And this is something that has also come up in our podcast conversations, how there's a lot of misunderstanding about what the current state of brain-computer interface technology is. So Stephen Rainey, for example, talks about how we're nowhere near having BCIs that can actually read minds. He makes a distinction between neural decoding and mind reading. So we're getting closer to neural decoding machines, not necessarily mind reading machines. So I think educating the public, making sure the public has realistic kind of expectation and understanding where the technology is important in guiding the future of this technology. That said, I think it's also important to think about futuristic use cases and how things can go wrong. And so I'll now pass it off to Jay to talk about some of those futuristic use cases.